The true false questions for this one are pretty good. So I like these ones. The first one says, if you increase the sample size, all other values remain the same. The width of the confidence interval will increase if you do that. And they were supposed to say true or false. Okay. So in approaching this one, I wanted to look at the confidence interval formula. And so we've got a couple different confidence interval formulas. Actually, we got several different confidence interval formulas that she could be talking about. And the sample size is that square root of n. So all of them have that n underneath a square root sign somewhere in there. And she's saying that if you don't change anything else about the problem, but you make that n value bigger, then it would make the confidence interval wider. Okay? And the answer to this is false. But in order to understand how that's false, you have to understand how numbers work. And so off the top of your head, you might not be able to figure this out, but if you had a calculator, you could plug some things in and you could go, oh, okay. So I'll try and intuit the reason why the answer to this one is false. So if we leave this number the same, and we leave this number the same, and we leave this number the same, but we make this number bigger, you're dividing by that number. And even though it's underneath a square root sign, when you divide by that number, I just realized I didn't hit record, did I? Or no, I did. I'm good. Pause, stop recording. Okay, good. Jen's just like, anybody else's anxiety higher? Like going into the finals week? I'm like definitely going all the time, and I'm not even taking the finals. It's just helping you guys prepare. Okay, I'm recording. So if we're taking a look at the formula as a whole, the fact that n is down in a denominator when we do this. And the way she writes the formulas on the sheet, I understand because that's just kind of how the type works, but I'm going to rewrite one of the formulas in a way that you might be able to see it a little bit better. So I'll do the one with the z. X bar plus or minus the z alpha over 2 times the sigma. And then in the bottom is the square root of n. And so you could actually put this together like this. This would be the same thing as X bar plus or minus. The Z alpha over 2 is up in the numerator with that with the sigma up there. And the square root of n is actually down in the bottom. These are equivalent formulas to each other. And the reason I'm just rewriting it like this is so that you can see that the n is really down in a denominator. And so even if it's underneath a square root sign, if that n gets bigger, taking the square root of that number still makes that square root number a bigger number than it was before. So like, let's say that the number down here was 25 before. When you take the square root of 25, you get 5, okay? But if I make this 100, taking the square root of 100, we get 10. The number got bigger. So when we made the n bigger, the number in the bottom got bigger. When the number in the bottom gets bigger, the overall fraction gets smaller. So an example of that would be like if we had 20 over 10 versus 20 over 20. 20 over 10, if I divide that, I get 2. When I make the bottom number bigger, 20 divided by 20 becomes 1. When the number in the bottom gets bigger, the overall fraction gets smaller. So as that n increases, this part of the confidence interval becomes a smaller number. So that means that you're taking your x bar and you're adding and subtracting a smaller number than you were before. So like, let's say that your original x bar, let's just come up with a number for the x bar. Let's pretend x bar was 10, okay? If x bar was 10, then I'm adding and subtracting a smaller number than I was before. So let's say first time I'm doing 10 plus or minus, we'll say 10. And then the second time I'm doing 10 plus or minus a smaller number, let's say 5. If it's 10 plus or minus 10, then one of the times we do 10 minus 10 and we'd get 0. And one of the times we'd do 10 plus 10 and we'd get 20. And if it's 10 plus or minus this smaller number, one of the times it's 10 minus 5, that would give us 5. And one of the times it's 10 plus 5, that would give us 15. And so see how in our original, we actually had a wider confidence interval. We went from 0 all the way to 20. Now we're just going from 5 to 15. This is a smaller or a less wide confidence interval. Is that okay? So the question is saying, if you increase the sample size and all other values remain the same, the width of the confidence intervals will increase? The opposite happened. The width of the confidence interval got smaller. So we're going to say false. And then she wants you to give a reason. And I would say the error term sigma divided by the square root of n decreases when n increases. And so when that error becomes smaller, then we're adding and subtracting a smaller number than we were before, and that actually makes it a less wide confidence interval, not a wider one. Is that okay? So how could she change that question? Because usually she's not going to give you the exact same question, but she might give you some variation on this. She could say something like, if you decrease the sample size and all other values remain the same, the width of the confidence intervals will increase. True or false? If you decrease the sample size, then yes, this is true. If you decrease the sample size, then that would mean that that n value gets smaller, which would mean the error term gets bigger. And so you'd be adding and subtracting a bigger number to your x bar, and that's going to make you have a wider confidence interval. So she could change the question by changing one word, and then it would change what you would say. So if it said, if you decrease the sample size, all other values remain the same, the width of the confidence interval will increase, then this would be true instead of false. Is that okay? All right, the next one says, if you take large random samples over and over again from the same population and make 95% confidence intervals for the population average, about 95% of the intervals should contain the population average. True or false? And I saw someone showed me the notes that she did from that day where she drew out intervals, and almost all of them included the population mean that we were talking about, but like one of them didn't or something. She drew them all out and then like one of them didn't. So what this is talking about is literally the definition of a confidence interval. So this one's true. If you take large random samples over and over again from the same population and you make 95% confidence interval, then the definition of a 95% confidence interval is about 95% of the intervals that you make with those samples should contain the population average. So this one's true because it's the definition of a confidence interval. How could she change this question? The typical way that I see people try and trick students with a confidence interval question is, if you take large random samples over and over again from the population, and it's a 95% confidence interval, they could say something like, there's a 99% probability that the true population mean falls in your confidence interval. And the answer is no. It's literally this. And so if you're like, well, how will I prepare for that? I'd say, like, memorize that line. That's the definition of a confidence interval. And so you want to actually make 95 like, or actually 100 different confidence intervals, 95 of them will contain the true population mean. That's just the definition. Yeah.
So if they were like small samples, or if they were from different populations.
She's not going to probably change the wording up that way, but yes, it would make a difference if they were not big samples. Big samples are definitely the reason why we can come to this conclusion. But the way that I normally see people change this one is that instead of you having to have 95% of the intervals containing the population mean, they'll say something like, there's a 95% likelihood that the true population mean is in the confidence interval, and that one's false. So that's normally how they flip it. From the same population, that would be important, because if we're talking about completely different populations, then what are we even talking about? It has to be the same population, or we can't draw any conclusions if we're just talking about a bunch of different random populations of a thing. So, good question. This would matter. If you change that to small and you change that to a different population, then yeah, that would be different. Question.
Kind of similar, so it wouldn't change if, like, say it was 90%, it would be the same rule.
Yep, you would just change that number to 90%, so you'll keep it the same. But yeah, same definition. Good question. All right. The next one is the one that most people sent me panicked emails about. Jen, we didn't learn how to do this. I was like, well, I saw in your notes where she had like a brief moment of it, but I don't remember helping anyone with a homework question on this, so we didn't get a lot of practice on it. Let's talk it through. A certain question on a test is answered correctly 22%. Oh, by 22% of the respondents. Okay. Estimate the probability that among the next 150 responses, there will be at most 40 correct answers. Round answers to 4 decimal places. We got a heck of a lot of hints in here on what it is she wants you to do. The hint that I got, the fact that we're talking about a percentage of things tells me we've got a P happening. And when we talked about P's happening, we also talked about situations where only one of 2 things could happen, and we called that binomial distributions. And so here, when I look down here and it says that on a test, this particular question is only answered correctly by about 22% of the respondents. The only options are it was answered correctly or it was answered incorrectly. 2 things could happen. They answered it correctly or they answered it incorrectly. Makes me think, we're in the land of binomial things. When we did actual binomial things, she didn't say approximate. The fact that it has approximate in here tells us that this is a binomial approximation to a normal problem. So I need some other information to help me do my setup on this. Is this anywhere on your formula sheet? The answer is no. So that's why I was like, oh, surprised to see this on the practice exam. So we didn't really have homework problems on it, and it's not on your formula sheet. So I don't know how comfortable you guys feel about this one. So we're going to talk through how I would like write out what we've got. I can see that I have a P of 0.22. If it's a binomial situation, we have P's and we have Q's, or we have 1 minus P's. That's the same thing as a Q. So I'm going to go ahead and go find my Q, which is also 1 minus P. If my P is 0.22, then my Q is 0.78. Okay. We also got an N. They told us that there's 150 responses. And so when we have n's and p's and we're talking about binomial things, we had to check. There were certain conditions we needed to check with binomial things. And one of them was we had to check that n times p was greater than or equal to 10. And we had to check that n times 1 minus p was also greater than or equal to 10. And if we met those conditions, then we're allowed to use our binomial tools for this. So n times p is going to be 150 times 0.22. 150 times 0.22, we just need it to be bigger than 10. So I'm going to say 150 times 0.22 is 33. So I'm going to put a little check mark after it because we met that condition. And then n times 1 minus p is 150 times our q value, which is 0.78. I just need that one to be bigger than 10 as well. So this is going to be 150 times 0.78. This comes out to be 117. So we met the conditions to be able to use our binomial approximation to the normal. So what that means is we're allowed to use the normal distribution table, which is our z table. So that means we need to go find a z-score. When we find a z-score, we do our x minus our mean value. And let's see, in this case, I didn't write those down, so we'll take care of that in just a second. And then we divide it by our standard deviation. And let's go find those numbers because we don't actually see those here. On a previous formula sheet, so not the one that she gave you for this exam, but for one of the previous exams, she gave you how to find the mean and how to find the standard deviation for binomial things. So I'll write those down. To find the mean for a binomial thing, we do the n times the p. We already did n times p when we were checking to make sure that it was bigger than or equal to 10. We figured out that was 33. So we have that our mean is 33. The standard deviation formula that was on the formula sheet for last time is the square root of n times p times 1 minus p, or you could replace that 1 minus p with a q. And so for us, that's going to be 150 times 0.22 times 0.78. And then we're going to take the square root of that number. And I got 5.07. So those weren't things that were given in the problem. So if you're doing a binomial approximation problem and she doesn't give you the mean and she doesn't give you the standard deviation, then the formula for the mean is n times p. And the formula for the standard deviation is the square root of n times p times 1 minus p. She put that on a previous formula sheet. So I don't know if she's going to give you a new formula sheet because you guys were showing me one that looked like this and it didn't have that on there. So I'm a little nervous about that. But I assume if she's going to actually give you a question where you have to do that, that she'll put those formulas back because she gave them to you before. But I don't know. So that would be maybe a good question to email. Or just memorize these. They're not that long. Okay. So I have the mu and I have the standard deviation now. And so this x, that's the 40 in the problem, except there's this thing called a continuity correction. And I know that it's in your notes, but I don't know how much you guys talked about it. Does that sound familiar at all?
The 0.5 thing.
It's the 0.5 thing. How did you talk about that 0.5 thing? Did she draw you pictures or?
Those pictures. Do like, you wanna get the value in there as well, but like not.
Right. So the fact that this says, and I'm going to underline it since it's in there, it says that there will be at most 40 correct answers. What that means is we want the probability that X is, when we say at most, that's less than or equal to 40. Okay. In terms of how we figure out if you should be adding 0.5 or subtracting 0.5, I think of a picture. And when we're doing binomial distributions, there's all these bars happening. They kind of like binomial distribution things. You've got like these rectangles that are doing this stuff. It's not a nice smooth curve. When we talk about the normal distribution is a nice smooth curve. And so what we're doing is we're taking a distribution that actually has those crazy rectangles in it, but we're going to approximate it using our z table, which is the nice smooth curve. So that's why it's called the binomial approximation to the normal curve, because this is close, like it's kind of following that shape, but it's not exactly the same as the nice smooth curve. Like some of the rectangles aren't going to be exactly lined up with the smooth curve. So what we do when we're talking about 40 is I'm going to go ahead and I'm going to create like a little rectangle here. And along the bottom of the rectangle here, I'm going to put 39.5. And the other end of the rectangle here, I'm going to put 40.5. And right in the middle of the rectangles is always the whole number thing that we're talking about. That 40 is going to go right in the middle of the rectangle. So I'll put a little pink mark right there. That's the 40. And I'll zoom in a little so that we can talk about the adding or the subtracting part. Because this says we want P to be less than or equal to that 40, I want to include the 40 in the number. So if I added 0.5, I'd be over here at 40.5. And if I was at 40.5 and I need to do less than or equal to, that's going to allow me to, so like I'm doing less than or equal to that number. If you're at 40.5, it's going to include the 40 in the number. If I subtracted 0.5 from the 40, I'd be here. And if I have to do less than or equal, we're going to keep going this way. If I'm at 39.5, am I going to include the 40 if I'm doing less than? So we're looking at that sign. We're going less than the number. So if I start at 40.5 and I go less than, will I include 40? Yeah. If I start at 39.5 and I do less than, I won't include 40. So if I need to add or subtract it depends on if I wanted to include the 40 or if I don't want to include the 40. So the fact that the line is underneath there is saying we got to include the 40. So in order to do that, I want to start at 40.5. So I want to add 0.5 to my number. If she had turned that sign around, we would be doing a different thing. But the reason that we're going to go to 40.5 is it says include the 40. And I'm either going to add 0.5 or subtract 0.5. That's all we ever do in the continuity corrections. It's one of the two things. So that means you're either going to put 39.5 or you're going to put 40.5. If you want to include the 40, you can't start at 39.5 and go less because you're going to miss the 40, right? You have to start with the bigger one. Is that okay? So I'm going to do 40.5. We're going to do the add the 0.5 number to it. So we're going to use x equals 40.5 for the continuity correction. That's just the name of the either adding the 0.5 or subtracting 0.5. So I'm coming back over to the z. And for the x, instead of using 40, we're going to use 40.5. I guess I can zoom out now. I'm a little close. Okay. And then we're going to subtract the mu. We said the mu was 33. And we're going to divide by the sigma. We calculated the sigma was 5.07. Okay. So we're going to do 40.5 minus 33. So I got 7.5, and then we're going to divide that by 5.07. And I got 1.48 if I round it. 1.48. Now, we want there to be at most 40 correct answers. And we're using the normal distribution curve to help us make an approximation here. The z value we got was 1.48. So remember, 0 is right down the middle. So 1.48 would be over here. So my z is 1.48 would be here. The table is always going to give you this side. So it always starts from the left and goes up to that number. So we got to figure out, is that the number that I want, or is it going to give me the opposite of what I want? Do I want the left tail or do I want the right tail? This says that we are estimating the probability that among the next 150 responses, there are at most 40 correct answers. So because, again, we've got that less than or equal to sign, then this is the side that we want. We want this side. So do we have to subtract our answer from 1 or no? No, we're good to go. The answer in the table for 1.48 is going to give us the p-value we want. So I'm going to write p equals, and then I'm going to go get my z table. And my z table for positive 1.48. 1.48 says 0.9306. Now, here's what's funny about this. It says round your answer to 4 decimal places. That was kind of a hint from her that that should be a thing that was coming out of your table exactly, because the table gives us 4 decimal places. Otherwise, your calculator would be doing something crazy and be like, what are we doing? You don't have to worry about that. The table gives you the number. So you haven't seen a whole lot of these. Couple things that I want you to try and keep in mind so that you even know. You don't want professional audio settings. There we go. If you're staring at one of the problems and you're like, how do I know this is a normal approximation problem? It's got to have a p-value in it. It's going to have a p and it's going to have an n. And the reason it's got to have a p and an n is that somewhere in the problem, you're checking n times p and you're checking n times 1 minus p. So you have to have a p and you have to have an n, or we can't check those things. Okay. You're going to need to probably on your own go find the mu and the sigma. If she doesn't give you the formulas for those things, that's a thing you're going to want to memorize. The mu is always n times p, and the sigma is always the square root of n times p times q, technically. That might be easier to memorize, but q is the same thing as 1 minus p. Once you've checked to make sure you're allowed to use the binomial approximation to the normal, which means you're just checking to make sure n times p is greater than or equal to 10 and that n times q is also greater than or equal to 10. As long as those conditions are held, then we're good to go make our approximation. And so that means because you're using a binomial approximation to the normal curve, that means that's the z table, always the z table. So you're going to find a z value. We just went and got the mu and we got the sigma. So then we got to figure out the X part. The X part's going to involve that continuity correction. So depending on what she writes in terms of if it's less than or equal to, or if it's greater than, let's think about what would have changed if it was just greater than. So let's say she had wanted us to do P, or the probability that X is greater than 40. What would have changed about our problem? I still would have drawn you the rectangle like this. And I still would have put 39.5 right here. And I still would have put 40.5 right here. And I still would have put the 40 right in the middle. So whatever number they're talking about, do minus 0.5 and plus 0.5 on a picture for yourself. And then the sign itself, if we just want X to be bigger than 40, that means I don't want 40 to get included. So your only choices are 39.5 or 40.5. You're just going to either add 0.5 or subtract 0.5. So don't make it more complicated on yourself and be like, it could be all these other numbers. It can't. It's just going to be either adding 0.5 or subtracting 0.5. If we don't want to include 40 and we're doing numbers bigger than it, if I start at 39.5, am I going to include 40 when I go bigger than it? So if I'm starting here and I'm going bigger, so I'm right here, am I going to pass 40 as I go? Yeah, shoot, I don't want to include 40. So don't start at 39.5. If you don't want to include 40, then that means you got to start at 40.5. And you only have two choices. You're either starting at 39.5 or you're starting at 40.5. You don't have any other choices. So you just literally, you're just doing this test with yourself of, oh, it's got to be bigger than that number. Oh, 39.5. Oh, shoot, I'll pass 40. I don't want that. So that means choose this one. You'll choose the bigger one. Okay, so we ended up choosing the same number when it was greater than. And so you might be like, whoa, wait, that's weird. But watch what changes if I put a line underneath it. Greater than or equal to 40. Now, if I want to include 40, if I start at 40.5 and I have to go bigger than it, will I include 40? No, I miss it. So if I want to include 40, now I have to start at the 39.5. So by putting a line underneath it, now I'm choosing that one. Some people prefer to memorize the rules. I think it's a terrible way to do that, but I wrote the rules off to the side over here if you want to write them down. Here's the rules. It's based on the signs. So I put K's in there instead of the actual number. The K, you'd fill in the 40 for this particular problem, but it could be any number depending on the problem. If the sign is a less than or equal to sign, you're going to add 0.5. If it's a less than sign, you're going to subtract 0.5. If it's a greater than or equal to sign, you're going to subtract 0.5. And if it's just a greater than sign, you're going to add 0.5. I think it's a terrible way to do this, to try and do it by memorizing. I think it's way better to draw yourself the picture and reason your way through it, because it's really easy to mix up these rules if you're memorizing it. But some people really prefer to memorize it, and that's fine. So I wrote them there. That's the rule. Yeah.
The E supposed to be greater than or equal to 5 out of 10.
Is it?
I think so.
Was it 5? Jen might have messed it up. Maybe it's a 5. If it's a 5, I apologize.
Well,
Check your notes. Jen's probably, I could be wrong. It depends on the teacher, so I'm kind of mixing up rules that I've learned in the past. Could be 5. Really could be. In this particular case, then we totally met it. Definitely 33 is bigger than 5 and 117 is bigger than 5. So if it's supposed to be 5, that's fine. Yeah. It's 10. Whew, thank you. Some classes it is 5, I'm sure, and some classes it's 10. It just totally depends. Professors have different rules, but. How are you feeling about that one? It's a little weird. Next one. I was really glad she did this because I had made, remember I said I made 2 additional problems and we didn't get to them, but I posted the solutions in Canvas for you anyway. It was this type of problem was one of the ones that I put in there. And actually she included a sample size, which was the other type of problem I put in there. So she covered both of the things I was worried about. So if you go back to the notes from Tuesday and you look at the last 2 problems, I didn't do them with you, but I put the solutions in there. So you have 2 more practice problems that are like this one. So let's do this one, since this is the one she gave us. Okay. In a sample of 50 adults selected randomly from one town, it's found that 10 of them have been exposed to a particular strain of the flu. Assume each adult is independent of each other. Construct a 99% confidence interval for the true proportion of adults that have been exposed to the flu. Then interpret your confidence interval, and we're going to round the bounds to 2 decimal places. Okay, lots of words there. Let's write down what we got. We got a sample of 50 adults. So I've definitely got an n is equal to 50 scenario. Okay. And then it's saying that of those 50, 10 of them got the flu. So that's the p hat. That's the proportion. That's our sample proportion. You're going to put the 10 in the top over the 50 total to get your proportion. 10 out of 50. Usually when we do these problems, we turn it into a percentage. Can you do this in your head? Can you make this a percentage on your own without a calculator? Want me to give you a hint? You want the denominator to be 100. So if we made the denominator 100, we'd have to multiply by 2, right? So if we multiply by 2 here, we'll get 20. So this is 20%. So I'm going to write it as 0.20. But I promise if I put this into my calculator, I'll prove it to you. Jen didn't make this up. 10 divided by 50 was 20%, 0.20. Okay. We're going to need a 99% confidence interval in the formula for a confidence interval for a proportion. We've got a z alpha over 2 thing in there. So we need a special z for a 99% confidence interval. The z alpha over 2 for a 99% confidence interval. If you look at that cute little cheater box at the bottom of your z, this is your z table. The cheater box down here says for a 99% confidence interval, the number we want is 2.575. So I'm going to write that down, 2.575. Cool. All right. Now I'm going to write down the formula that was on her formula sheet. We're going to put p hat plus or minus the z alpha over 2 times the square root of p hat times 1 minus p hat divided by n. Okay. So p hat plus or minus the z alpha over 2 times the square root of p hat times 1 minus p hat, all divided by n. There's our formula. We've got all those numbers, so I'm just plugging those in now. So 0.20 plus or minus, that z is 2.575 times the square root of 0.20 times 1 minus 0.20 divided by 50. Okay. I'll multiply that part out. Square root 0.2 times 0.8 divided by 50 times 2.575 gives me 0.145. All right, 7. Okay. So one of the times I'm going to do 0.2 minus this number, and one of the times I'm going to do 0.2 plus this number, and that'll give me my confidence interval. So the smaller bound is 0.05. And the bigger one is 0.35. Okay, so my confidence interval is 0.05 to 0.35, but then it says interpret that confidence interval. So I'm going to say we're 99% confident. That what? The true proportion of adults exposed to the flu is between, and now I'm going to write these as percent. So if I move the decimal point over 2 places, this becomes 5%. And if I move this one over 2 places, it becomes 35%. So we are 99% confident that the true proportion of adults exposed to this flu is between 5% and 35%. Okay. That's a pretty wide confidence interval. So let's look at the next question. Does this interval support the claim that the true proportion of all adults exposed to this strain of the flu is 15%? Why or why not? What would you say? Pretend this is your test. You've done all the hard work. This part's not actually supposed to be a hard question, but this stuff messes people up a lot because they're like, I don't know what it wants. I don't know, Jen. What do we think they're asking us?
Whether it's a point, null hypothesis or not, the claim.
Oh, we didn't even have a null hypothesis, but I like that idea. It wants to know about this confidence interval. And so what are we looking for? Did you hear that? If the 15% that they're asking about is in the confidence interval you just found. So we said that the true proportion of adults exposed to this flu is between 5% and 35%. Is 15% in that range? Yay! So we say yes. Yes, this does, because 15% is in that confidence interval. Okay, I'm gonna skip down to question D for just a second. Because question D is related to question A, so I don't know why it's in this order. So we'll just skip to the one that we can already answer. From your confidence interval in part A, which we said was 0.05 to 0.35 or 5% to 35%, what is the smallest proportion of adults we expect to be exposed to this strain of the flu? Again, this is not supposed to be a hard question, but it trips people up because they're like, I don't know what it wants from me. I promise it's not a hard question. You wanna try?
I think it's 5%.
It is 5%. It's not hard. It really isn't. But if you don't know what it's asking, it feels scary. You're like, I don't know what it wants. And it literally just wants the smaller number on this confidence interval. So it's 5%. Yep. Good job. Okay. That one was easy. We got a little more work to do in part C. It's not hard, it's just a little more work. If you wanted to be 95% confident that the interval is accurate to within 2 percentage points, how large should your sample size be? This one, at the bottom of her formula sheet, she's got 2 different sample size formulas for you. She has a sample size formula for when we're talking about means, and she has a sample size formula for when we're talking about proportions. So we want this one because we've been talking about a sample proportion. So we want this formula here. So we need a z alpha over 2 squared times the p hat, which we already have, times 1 minus the p hat. We already have that as well. And then we're dividing it by the error squared. The error is the part where it says within something. Within 2 percentage points. Here's the way that you can miss this question because it's a little tricky. And the first time I did it, I didn't read it very carefully and I messed it up. So it's tricky. You have to read it carefully. When we talk about percentages, I don't use 2. If it's 2%, what do I write?
0.02.
Perfect. So that's how you could screw this one up. If at the bottom where the error is, you put 2 down there and you square it, you're going to get it wrong because it says percentage points. So we want to turn it into 0.02 and square that number. The first time I did this, I was like, that can't be right because I got a number that was like a tiny decimal number and I was like, the sample size is a tiny decimal? That don't make any sense. If I turned it into 0.02, it made perfect sense. So that's what we want to do. So I'm going to write the formula down. It's n is equal to the z alpha over 2 squared times the p hat times 1 minus p hat. And then we're dividing that by the error squared. I'll put it in parentheses just because I put everything else in parentheses. 95% confidence interval means the z that I want to use, if I use that cute little cheater square in the bottom for a 95% confidence interval, I want to use 1.96 as my z. So I'm going to use 1.96 and we got to square that number. The p hat we said is 0.20. Times 1 minus 0.20. And then in the bottom, this is where Jen made the mistake. I put 2 squared down there. That's not 2% though. I need to put 0.02 and square it, and then we'll get the right number. Okay, so 1.96 squared times 0.2 times 0.8. And I'm going to divide that number by 0.02 squared. And I got 1,536.64. And if you write that down, you'll be wrong because we want the smallest number of people you gotta ask, or the smallest number of people for our sample. The sample can't be a decimal. So what's the smallest number of humans we would have to ask? My hint is you can't have 0.64 of a human.
1,537.
Ding, 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 ding. So whatever this is, even if, so like this one wouldn't normally trip people up because the decimal point after this is 5 or bigger, so people would have rounded up anyway. But if this said 1,536.2, you still round up. So this is not a rounding question, this is a humans question. If you need a minimum sample size and it's telling you you have to have more than 1,536 because it's 1,536 and a decimal of a person, we need a whole other person to make it work. So even if that decimal point was like a 0.2, you'd still round up to the next person. Does that make sense? Sample size is not exactly the same as normal rounding. We want the next whole person. So we're going to make this 1,537 for the sample size. So I'm going to write, if you get a decimal, always round up. So it doesn't matter what the decimal is, we always round up. All right. We're going to end on a problem that's just like lots of the practice problems we've already done. So we'll end on a good note. Hopefully you'll feel more confident about this one. Also, it's about puppies. Suppose you're thinking about getting a puppy, but want to estimate the average number of minutes per day you will spend caring for the puppy. A random sample of 30 owners had a sample mean of 140 minutes with a standard deviation of 25 minutes. Assume the time spent caring for a puppy follows a normal distribution. Test the claim you will spend more than 125 minutes on average caring for the puppy. All right, there are a lot of words in there. We're gonna write down what we got. Okay. A random sample of 30 owners, that's an N. We got an N is equal to 30. Okay. They told us that there's a sample mean of 140. So what symbol is that? Beautiful. That's an X bar. Okay. And then they said that particular sample, even though they didn't write sample standard deviation, they're still talking about the sample because they said the sample of 30 owners had a sample mean with a standard deviation, even though it didn't say that it was a sample standard deviation. This would still be an S. It's 25. So this is a little tricky in that they didn't tell you the mu necessarily in the normal way we would say a mu, but it says test the claim that you'll spend more than 125 minutes. And whenever we do the claim, that's part of the hypothesis testing part. And the hypothesis has the 125 in it then if they're saying test that. So that means even though they didn't tell you that the population mean is 125, they're implying that by saying that's going to be part of the claim. So the first part of the question says state the null and alternative hypotheses and then mark the claim. So our HO and our HA. The HA is the easier one to write right now because it says test the claim you'll spend more than 125 minutes. So that would be that the mean is greater than 125. And that's the claim. They just told us it's the claim. That was nice of them. The claim is the thing you're testing. So you'll see if you went to go like pull up the notes from last time, I mismarked the claim on question 3 on Tuesday. I mismarked the claim on question 3 on Tuesday. The thing that we're testing is going to be the claim. I was thinking too fast. The claim for that one, if you have your notes in front of you, that should be the alternative hypothesis is the claim. I had marked it on your null hypothesis. Should be the alternative hypothesis. Calculate and interpret the test statistic. Round to 2 decimal places. Okay. This is either going to be a T or it's going to be a Z. How do I figure out which one?
For the T distribution, sigma's unknown.
Correct. Do we have a sigma? We do not. We don't know it. Cool. So this is probably going to be a t distribution. If it's a t, then our formula doesn't look that different than the z, honestly. You're still going to put your the x minus the mu. It's going to be divided by s over the square root of your n. What would be different if it was a z? Instead of the s, you'd have a sigma in there, is all that would change about that formula. Okay, so if we plug in our numbers, we're going to get 3.29. If we round it to 2 decimal places. Okay. It says calculate and interpret this test statistic. Whether it's a t or it's a z, what we're looking for is this number positive or is this number negative? If it's positive, we're going to say it's above the mean. If it's negative, we're going to say it's below the mean. So we're going to say that this is about 3.29 standard deviations above the mean because it's positive. Question. When we talked about standard deviations, being 1 standard deviation away wasn't that unusual. We said that that was like your b value and your d value, right? Because your mean is supposed to be the c. So then if we went out 2 standard deviations, that became your a value and your f value. So that became more unusual. When we were at 3 standard deviations, started to be pretty crazy, right? We're more than 3 standard deviations away. So we have a pretty unusual number happening here. So when you get your t or your z, if your t or your z are really big numbers like 4 or 5 or 6 or whatever, you should be going, oh, I'm about to get a very unusual p-value here. So keeping that in mind, it wants us to calculate and interpret the p-value. If this is a t, what do I need in order to look on my t-table? Degrees of freedom, right? So degrees of freedom for this one, it's always n minus 1. Our n was 30. So we have 29 degrees of freedom here. Okay. So I'm coming down to 29 degrees of freedom. And the number that we got, I'm covering it up, but we said it was 3.29. Okay. So at 29 degrees of freedom, 3.29 is between these two numbers here, the 2.756 and the 3.396. Is that okay? 3.29 is between those two? Okay. For this hypothesis test, was this a 1-tail test or a 2-tail test? And how do you know? It was 1-tail. Why was it 1-tail? Because it said that we just wanted greater than 125. Oh, sorry, you can't see it. One more. Greater than 125. So just one direction. This is a 1-tail test. So if it's a 1-tail test, and when we come up between these two numbers down here, I'm going up to the line that has 1 tail on it, not 2 tail. So I'm going up to those two numbers right there. So you're going to say that your p-value is bigger than 0.001, but it's smaller than 0.005. Whenever we use the t-table, you don't get to give me an exact t-value or exact p-value unless we happen to be really lucky and our number matches one of the numbers in the table. It hardly ever does. So you're almost always going to give a range. So we're going to say it's between those two numbers.
If the table ends at say like the 0.005 column, what would you do? Like there's not the 0.001 and then point.
So are you saying like, what if your number was like 4 or something? And so we were falling off the edge
Yeah.
here? Then that means that it has to be smaller than even the smallest number it's showing on the table. So in that case, you wouldn't be able to bound it necessarily, but generally speaking, she'll let you bound it. Yeah.
So, why is it smaller than like the 0.05, the 2 point, or 3.29 falls like smaller? Oh, never mind.
So you're going, so the 3.29 is between these two numbers. So between those two numbers means we're going to use these ones and you're going to say it's bigger than this one because this number is smaller than this one. So you're going to say bigger than this one, but smaller than this one. Yeah. So I'm going to write that down. I'm going to say P is greater than or equal to 0.001, but it's less than or equal to 0.005. And that's coming straight from the table. It says sketch a graph to support your work. Sure, we could do that. So if t is equal to 0 is right down the middle of the distribution, this would be like 1 standard deviation away. This would be like 2 standard deviations away, 3 standard deviations away. So we're like hecka at the end of this tail down here. This is my t is equal to 3.29. And it wants more than 125 minutes. So literally it wants this tiny amount that's over in the bottom of that table there. Okay. That matches up with this p-value being hecka tiny. The fact that we just got hecka tiny p makes sense based on that picture. So I can't tell you exactly what the p is if we're using the t-table. I can only tell you that it's got to be bigger than this number, but smaller than this number. If we actually had a computer program, it would tell us the exact p, but we don't have that. So when she is asking you a t-table question, you can only bound it. So it says state your conclusion at the 5% significance level. That means your alpha is equal to 0.05. So we're looking at our p-value. You don't have an exact p-value, but you know that the absolute biggest it could possibly be is that number right there. This number looks a lot like this number, but there's an extra 0 in there. So this one's heck smaller than this one. We want the p to be smaller, and it is. So what are you going to say? You reject the null hypothesis. Since our p-value is less than alpha equal 0.05, we reject the null hypothesis. Okay, so if we reject the null hypothesis, oh, I didn't actually write down the null hypothesis, did I? I wrote down the alternative hypothesis and then I quit. You have two choices for your null hypothesis. We could either just turn this sign around, which is usually what I do. So I'll make it less than or equal to 125. Or you could say that it's just equal to 125. Both are okay. We're rejecting that that's the case. So that means we do have sufficient evidence to support that it's going to take you more than 125 minutes to take care of your puppy. So I'm going to write, there is sufficient evidence to conclude that you will spend more than 125 minutes on average caring for your puppy. All right, how do you feel? Nervous still? Normal to feel a little nervous. Questions?
I think she wants us to interpret the p-value also. And she wants us to write a statement about it.
Statement about the p-value?
Like, and for example, she's done like, if the null hypothesis is true, then the true mean like spent pairing would be.
Oh, so if the null hypothesis were true, then the true mean probability that the time spent pairing will be more than the 125 minutes. You're gonna have to give a range on this one.
Okay.
Is going to be between I guess you could move it over and make it 0.1% and 0.5%. So it's a very small amount. Very small amount.
I'm sorry, so you said to interpret that, we would say that we would just have to like write it out in words.
So if the null hypothesis were true, then what is a p-value? It's a probability. So the p is coming from probability. So when it says what's the p-value. So if the null hypothesis were true, then the probability that you're going to spend more than 125 minutes caring for your puppy. Sorry, not more than. We're talking about the null hypothesis. The null hypothesis was the either equal to or less than or equal to would be between, and then if you move that decimal point over 2 places, you could say 0.1% and 0.5%. Since that's so unlikely, in this next line, because that p-value is so small, we're going to reject that null hypothesis and we're going to say that that probability is too small. So because that probability is so small, there is sufficient evidence to conclude that you'll actually spend more than 125 minutes a week caring for your puppy. So what this percentage here is showing you in the tail in the picture is that if the null hypothesis is true, that's the likelihood that you're going to be spending less than 125 minutes a week caring for your puppy. That's not very likely based on that picture, right? It's looking hecka more likely that you're going to spend more time than that.
So they were to ask us like what type of error we would do it with like type 1 error because we could spend more time. And it's saying that.
So your type 1 error would be that your probability that you said that your null hypothesis was false, given that it was actually true. We just said that the null hypothesis was false, right? So then yes, you're talking about your type 1 error. Good, good. Oh, did she never even do to talk about type 1 or type 2?
Like last lecture, like going to go into it and just.
Oh, well then, I guess maybe you don't have to worry about that so much. Sorry, I spent so much time on it then. Oops.
Let's do, sorry, we're after the tiny bit, did you do the 2 problems from last time?
I did not do the 2 problems from last time. So what I said was I was really excited that she chose in problem number 3 to do a proportion problem. because the two problems I picked, one was a proportion problem and the other thing that I picked was a sample size problem. So we went over these ones and then I said, I wrote up the solutions to those ones on the notes for Tuesday. So if you want to use those as like extra practice problems for yourself, those solutions are up there. Yeah. They'll probably feel better now that you're like, all right, we did one of these.